Last class, we had a brief historical introduction to the history and the development of the field since ancient times. And what we'll do today is we'll first look at the different channels of information by which astronomers study the universe. And then we will focus on different aspects of it over the next couple of classes or so before we move on to other aspects of the field. And as you saw yesterday in the last class, that since millennia, man was confined to looking at the universe largely through the optical window of the electromagnetic spectrum. And it was only till about the early 1930s when the electromagnetic spectrum began to be extended out well beyond the optical region of the spectrum. But this started off a little while earlier with William Herschel's serendipitous discovery of infrared radiation in sunlight. For example, what he did was, using a prism, he just split the sunlight into its different wavelengths or frequencies, which we perceive as different colors, and we put a thermometer beyond the red end of the spectrum. And he realized that there was emission beyond it as well. And that was how he discovered that there is emission from the sun itself, which extends beyond the visible region of the electromagnetic spectrum. He really didn't put a thermometer at the other end, at the ultraviolet or beyond the violet end, but that was left to Johann Wilhelm Ritter, a German scientist, who found the ultraviolet emission about a year later, putting chemicals over there and looking at the chemical effects of ultraviolet radiation. And he, for a while, called it chemical rays. So today we know that these were the early forays into the beyond the visible region, into the infrared and the ultraviolet region of the spectrum, showing that the universe emits radiation outside the visible range as well. Now, modern astronomy uses a very wide range of channels. So I would like you to sort of just briefly mention what do you think, what are the different range of channels which modern astronomy uses? Any one of you can unmute yourself and say.
Radio waves?
Radio waves, okay. That is part of the electromagnetic spectrum.
Sir, from what I've seen, more or less every wave on the electromagnetic spectrum is used to some extent.
Yes, every wave in the electromagnetic spectrum is used. That's absolutely correct. What else?
Sir, Doppler shift of some wavelengths coming to Earth is used to measure how fast it is going or how fast it is moving away from us.
Yes, Doppler shift can be used, is used. Doppler shift is used, but it is still the electromagnetic spectrum that is used for Doppler shift measurements. For example, if there is a spectral line, then the spectral line will shift depending upon how fast the object is moving, with the shift being sort of related to the velocity at which the object is moving, either towards you or away from you. Now,
also we use gravitational waves nowadays.
Gravitational waves, very good, very good. Gravitational waves. What else? Okay, so let's just have a look at the list. Okay, and as you correctly said, that electromagnetic radiation extending from the gamma rays at the highest energies, which means the shortest wavelengths, to radio waves, which are the longest wavelengths and the lowest frequencies. So as you can see, because frequency is related to energy, the energy also goes upwards compared to radio waves to gamma rays. Okay. Then in addition to that, astronomers get information about the universe from cosmic ray particles. What are cosmic ray particles? These are essentially high energy particles consisting of electron, protons, alpha particles, and heavier nuclei. The bulk of it, a lot of it is protons. And these are, depending upon the energy of the cosmic ray particles, they are generated in different processes. The highest energies that we observe today could be even coming from active galactic nuclei outside our galaxy, but some of the higher energy cosmic ray particles are perhaps born in exotic events, like when a massive star explodes. Supernovae could be creating them. Even stars like our sun or more massive stars generate cosmic ray particles, but they are at the lower end of the spectrum. So this is something we will look at in a bit more detail later. Today, we are just listing the different kinds of channels of astronomical information. The other aspect is neutrinos and antineutrinos. There are three types of neutrinos and antineutrinos associated with electrons, mu mesons, and tau mesons. And these have been actually very important in trying to understand, for example, the standard solar model, models of stellar evolution. And again, neutrinos we'll look at in more detail, but their interaction cross-section is extremely small. So it is very difficult to actually detect neutrinos. And one of the outstanding challenges of understanding the standard solar model was that the number of neutrinos which were detected were smaller number than what was predicted by the standard solar model. And it was later resolved by realizing that the neutrinos can actually change flavors. They can change from one type of neutrino to another type of neutrino as they propagate, and this is what is referred to as the changing of the flavor of the neutrinos. And the initial experiments were not actually sensitive to the different neutrinos. And the Sudbury Neutrino Observatory was one which played a leading role in resolving this issue, for which a Nobel Prize was also awarded. Besides electromagnetic radiation, cosmic ray particles, and neutrinos and antineutrinos, and gravitational waves, which one of you mentioned, another important component which brings us information is just solid constituents. You've all heard about lunar samples. You'd have all heard about meteorites, for example. And in fact, the age of the solar system has been determined from studies of the ages of meteorites. And now we also have asteroid samples. There have been spacecrafts which have landed in asteroids and are bringing back samples. Besides that, spacecrafts also, the grains of interstellar dust from which you can sort of try and infer what are the constituents of the dust grains that make up the interstellar medium of our galaxy. So you can see that this just gives you a flavor of the wide range of information which we get by looking at different components of the interstellar medium. Now, for example, cosmic ray particles, they are high energy particles, they move around, the charged particles will move around in the magnetic field of our galaxy. So even if they originate from a particular source, because they move around in the magnetic field of our galaxy, which has a uniform component, but also a random component along with it, that it is very difficult to trace back the origin of these cosmic ray particles, except for the very highest energy ones. And that is also something we will discuss when we have a brief look at cosmic ray particles. So we'll not look into great detail because this is not a very long course, but at least I'll give you a flavor of it to whet your appetite so that you can read and study more. And we can also have tutorial sessions where you can ask your questions if you want some of the aspects to be answered in a bit more detail. Now, if we look at now, what we will do is that today we will try to focus on the ultraviolet and visible and infrared part of the electromagnetic spectrum. And we are clubbing these together because the techniques are largely similar, okay? And then we will have a look at both the high energy part, gamma rays and X-rays put together, and the millimeter and radio waves put together, okay? So now let's look at the visible range of the electromagnetic spectrum. Now this is a plot of the transparency of the atmosphere, okay, across the entire electromagnetic spectrum, right from high energy gamma rays and X-rays at the lower wavelengths over here, and the optical is shown by the spectrum over here. Then as you go to longer wavelengths, you will come to the infrared, and then you will come to the radio, okay? Now you can see that except for the optical part and the radio part of the electromagnetic spectrum, okay, where you have an optical telescope schematically shown over here at the lower figure, and you have a radio telescope shown over here schematically, that you find that the bulk of the electromagnetic spectrum is actually either completely opaque or partially opaque to the radiation that comes from us from celestial objects. The bulk of the absorption or the cutting off the radiation is due to water vapor and molecules in the atmosphere, carbon dioxide, etc. And except in the optical region of the spectrum and the radio region of the spectrum. Okay. Now, it is worth sort of mentioning over here that when you look at the optical region of the spectrum, that is what is also our eyes are sensitive to. And that is, and coincidentally or otherwise, that is also the region where the black body spectrum of the sun peaks, roughly. Okay. And we will see later that the spectrum of a star can be approximated by a black body spectrum. So this is where the sun peaks. And if the sun had actually peaked at a completely different frequency, for example, in the ultraviolet region of the spectrum, if it was a more massive star, then the radiation would not have come through. And life itself, questionable whether life itself would have been possible as we know it today. And also the fact that we are able to see in this region of the spectrum, that must be due to the biological evolution of the human eye. But it is quite fortuitous that the region where the electromagnetic spectrum for observations on the Earth is transparent is exactly lies in the region where the black body spectrum of the sun peaks. Again, when you come, as I said, in the radio region of the spectrum, okay, over here it is given as a few centimeters to about slightly over 10 meters as the range over which you can observe it, that the atmosphere is transparent. The radio waves come through. But the longer wavelength radio waves you can see over here, they are again blocked out. So what do you think blocks out the long wavelength radio waves? Any one of you can unmute and say, what blocks out the long wavelength radio waves? What are your suggestions?
So maybe it gets reflected by the atmosphere.
Reflected back is okay, but not the atmosphere. Think a little bit more.
The magnetic field.
Sir, the magnetic field around the Earth.
I mean, electromagnetic radiation will pass through if there is a magnetic field, right?
Yeah, exactly. The magnetic field, I think, will play a bigger role for the cosmic ray particles than for the radio.
Well, you're getting warmer, but think of what lies beyond the atmosphere.
The ionosphere?
The ionosphere. Okay. So what happens is that when a radio, the ionosphere is basically a plasma, right? It is ionized. It consists of electrons, protons, and associated with every plasma, there is a plasma frequency, which depends on the electron density. Now, if your frequency is lower than the plasma frequency, then the wave is not going to propagate through. All right. Some of it could be absorbed, some of it could be reflected back. So the ionosphere is the one which actually blocks out the long wavelength radio waves. But there could be interesting physics to be learned from these long wavelength radio waves as well. And one way of doing it is to observe from space, or there's always been a talk about putting a telescope, a radio telescope on the far side of the moon. So you're not sort of affected by interference which comes from the Earth, and you can observe the universe at very long wavelengths. I don't think it'll happen in my lifetime, but perhaps someday that we will probe interesting physics at the very long wavelength region of the electromagnetic spectrum as well, at long wavelength radio waves. Okay, so the important thing to learn is the transparent at two bands, the optical and the radio. And for all other bands, you have to put observatories or telescopes outside the atmosphere. And for example, even in regions where it may not be completely blocked off, for example, in a millimeter wave region of the spectrum, where the water vapor can affect the signals coming in, that you'll find that these telescopes are usually put high on mountaintops, atmospheric effects are minimized, and also regions which are very low humidity and are dry. One of the very powerful millimeter wave telescope, ALMA, the Atacama Large Millimeter Array, is, for example, high up in a desert, which is effectively dry. This actually shows the same aspects which we discussed a short while ago, just that when you have to go above the atmosphere using satellites, rockets, even aircrafts have been used in the past. And also balloons were quite popular once upon a time, but now it has become more routine to put up satellites because one has really mastered the technology of putting these up in space. Now, this is something just to illustrate to you the range of wavelengths, the actual numbers that one is talking about. And here on the top panel, for example, from the radio to the gamma rays, the wavelength is given in meters, centimeters, and nanometers over here. In the visible region, you would find that people would often talk in terms of nanometers or angstroms. Whereas at radio frequencies, they would often talk about both in terms of the wavelength as well as in frequency. For example, there is a very important transition at 21 centimeters, which is about 1420 megahertz. Then observations at about 5 gigahertz is about 6 centimeters, 15 gigahertz is about 2 centimeters. So you can see that in radio, both frequency and wavelength is what will both be used, because these are all sort of manageable numbers to visualize as well. And in opticals, as I mentioned, often angstroms and nanometers are used these days. Whereas at the highest energies, people often talk about the energies, for example, keVs, MeVs, kilo electron volts, or mega electron volts, or million electron volts. And that is just the tradition of the astronomers who have worked in different fields. But obviously, using the relation between the velocity of light and the frequency and the wavelength, and also the relationship between the energy and the Planck's constant and the frequency, you can translate any frequency of an electromagnetic wave into wavelength and energy. But what I mentioned is what is normally used by the astronomical community, all right? And as we saw, this is a slightly outdated picture taken from the NASA website, that depending upon the wavelength, you would have to put certain wavelengths, you have to put telescopes outside the atmosphere. You can have ground-based telescopes at optical wavelengths and at radio wavelengths, but even at optical, our infrared, you can see that Hubble Space Telescope have made major contributions, and there are advantages of having a telescope outside the atmosphere, even in the optical region of the electromagnetic spectrum.